In section 1, we're going to be discussing the structure of organic molecules. Specifically, what we mean by structure is the Lewis structure, which represents the way that atoms are connected together to form a larger molecular structure. We're going to start with the Lewis theory of chemical bonding. Now, you have probably covered the Lewis theory and Lewis structures before, but they are centrally important in organic chemistry. And so we really need to have a deep understanding of them in order to work with them throughout the year and to communicate effectively. So although you may think you know everything there is about Lewis structures, trust me, I need you to know them even better. One of the important things about the Lewis theory that's kind of missed in the discussion is that the Lewis theory was really the first viable theory to explain why atoms formed bonds. Really, up until that time, there was no explanation for why atoms bonded together to form molecules. It's kind of amazing when you think about that the Lewis theory was published in 1916 during World War I, and in fact, 10 years after Einstein published his theory of relativity. So you can see that really much of organic chemistry and modern chemistry is very, very modern science. So, what did Lewis say? Well, Lewis focused on the question of why atoms form bonds. And basically, he had a theory that atoms wanted to have the same number of electrons as the nearest noble gas. So if we look at the periodic table, we can see that, for example, fluorine, which has 9 electrons when it's just an atom by itself, would like to do something in order to gain 1 more electron to have the same number as neon. Similarly, if we look on the other side, if we look at sodium, sodium would also like to have the same number of electrons as neon, which would mean that it would need to lose 1 electron. So in modern chemistry, since we know about bonding theory and orbital theory and everything, what we would say is that they want to have a completely full or completely empty valence shell, outer shell of electrons. Now, most main group atoms will try to have 8 valence electrons because if we look at the main group, so the main group is this section right here and that section right there of the periodic table that kind of sticks up above the transition metals and then also above the rare earths and lanthanides. So what we see here is that starting here, we could move to the left to become like helium, or move to the left to become like neon. So that would require emptying out our valence shell. On the right-hand side of the periodic table, we would rather add electrons so that we would become like the rightmost noble gas. So therefore, having 8 valence electrons is called the Octet Rule. Now, we're going to see that there are some exceptions to the Octet Rule. So for example, hydrogen only needs 2 electrons to become like helium. And so this is sometimes called the Duet Rule. And we're going to see that there are elements like boron and aluminum that are stable with only 6 valence electrons. And we call that an incomplete octet. And we'll go more into that later. So in summary then, why do atoms form bonds? Atoms form bonds in order to gain or lose electrons and thereby satisfy the Octet Rule. Now there are 2 types of bonds that we generally consider in chemistry. Those types of bonds come from 2 strategies for fulfilling the Octet Rule. So these 2 different strategies lead to the 2 main types of chemical bonds. The first type of bond that you're probably familiar with is what we call the ionic bond. In the ionic bond, we take two atoms. Now here, we're representing the atoms with what we call Lewis dot pictures, where we put a dot, which represents an electron, around the atom symbol. And we put as many dots as the atom would have in its circumstance. So for example, a neutral atom would have the same number of dots as it has valence electrons. So if we look, sodium has 1 valence electron, so it has 1 dot. Chlorine has 7. And what we can see is that sodium, it would be much easier for sodium to give away that 1 electron to become like the noble gas that's on the left on the periodic table. And chlorine would not like to give away 7. It would like to gain 1 electron to become like the noble gas on the right. So by putting these two together, they can work together. Sodium can give its 1 valence electron to the chlorine, completely transferring it. That's going to create a sodium that has effectively no valence electrons, or essentially has its previous inner core electrons become its valence electrons. And because now sodium lacks 1 electron compared to the number of positive charges in its nucleus, it gains an overall positive charge and becomes a positive ion. Similarly, chlorine, by gaining 1 electron, now has more electrons than it has charges in its nucleus, so it becomes a negatively charged ion. And these two oppositely charged ions then attract to each other. And we call this charge attraction the ionic bond. So we form oppositely charged ions, they're then attracted, and they form ionic bonds. The other strategy is to share the valence electrons between the atoms. Here's an example. These two chlorine atoms each have 7 valence electrons. Neither of them is willing to give up electrons to the other atom because they're so close. They really want to just gain electrons. So what they can do is they can move together so that they share electrons in the space between them. So this chlorine is sharing 1 electron into that. This chlorine is sharing an electron there. And what we end up with is, in this space, these two single electrons become shared between the two chlorines. If we then look at each chlorine atom, from its perspective as it looks out, it sees 2, 4, 6, 8 electrons. So it effectively believes that it has a complete octet. Now, one of the consequences of this is that the atoms must stay together in order to continue sharing these electrons. And so therefore, this becomes what we call the covalent bond. They're bonded together, they're stuck together because if they separate, they no longer share those electrons, and then they no longer believe that they have complete octets. So the strategy of forcing the atoms to remain in close proximity to continue sharing the electrons is called the covalent bond, which is really just abbreviation, co meaning together, valent standing for valence, so putting the valences together. Now, we're going to see that the Lewis theory is not 100% correct in all cases. It is, however, a very useful model which we can employ throughout the year to understand chemistry and to make predictions, even though in all of its details it's not perfectly correct. We are in fact going to slightly modify the model to make it cover more cases. So, one assumption that Lewis made about covalent bonds, which we've shown to be incorrect in some cases, is that covalent bonds are formed by sharing 2 electrons in the space between exactly 2 atoms. So 2 electrons, only 2 atoms. We call this type of bond a localized bond. But we're going to see later on that sometimes 2 electrons can be shared by 3 or more atoms all at the same time. We're going to call these delocalized bonds. And in fact, we're going to have to use resonance structures to describe them so that we can still use Lewis structures. Now, one of the questions then becomes, for a given pair of atoms, what type of bond are we going to have? The type of bond formed depends on the electronegativity difference between the atoms. So, just to review, electronegativity is the strength with which an atom attracts electrons. It's a periodic property. So, it's a property that depends on the location of the atom on the periodic table. And what we saw was that electronegativity increases as we move from left to right across the periodic table, which kind of makes sense if you think about that. Remember that the atoms want to, on the left side, lose electrons, so therefore they're not attracting electrons very strongly, whereas on the right side, they're very close to having the same number of electrons as the noble gas at the very end of the column, at the very end of the row, so they would like to gain electrons, so they're pulling very hard. We also see that electronegativity increases as we go up, and these are rough estimated electronegativity numbers. You're not responsible for memorizing these, you just need to know the trend. What we therefore see is that atoms with an electronegativity difference larger than about 2.0 form ionic bonds. If we look then at the numbers and where they are on the table, you can see that if you take an atom from the left side of the table, like sodium, and you pair it up with an atom from the right side of the table, like oxygen, that's going to cause them to have a very large electronegativity difference, in this case 2.6, which is much larger than 2.0, and therefore sodium with oxygen would form an ionic bond. In contrast, if we look at an atom like carbon and an atom like oxygen, you can see that they have an electronegativity difference of only about 1. So therefore, carbon and oxygen would form covalent bonds.